My name is Mengying. I'm currently a PhD student from Ghent University. Today, I'd like to demonstrate how the application of a cost-benefit analysis methodology helps decision-making when evaluating multiple design alternatives through a case study of passive fire protections in a 9-story office building. Fires in the buildings can lead to costly damage as well as injuries and deaths. Therefore, the fire safety measures are commonly used in the buildings to protect the buildings from fire and to limit the damage. However, the fire safety measures cannot fully reduce the risk to zero. Therefore, each design entails a radio risk. And whether this radio risk is acceptable depends not only on understanding the costs and benefits of fire protection measures, but also on assessing the perception of fire exposure. The key questions for the decision makers are whether the further risk reduction is necessary and if additional fire safety measures can be incorporated into design, and is it worth to invest in additional fire safety systems. For any design, the fire safety protections investment can be made. However, each investment comes at a cost, and as the safety level increases, the marginal benefits decrease. Therefore, a method is needed to solve these questions by evaluating the cost-effectiveness of fire protection investments, which is called the cost-benefit analysis. So the proposed methodology based on the calculation of the fire safety protections cost and the beneficial impact of the fire safety protections and the fire loss. First of all, the fire protection cost estimation is performed, which includes selecting the building categories and computing the cost of construction, the cost of implementation and maintenance of fire safety protections, and then computing the multipliers, which can represent the building in the selected building categories. Then the evaluation of fire losses is conducted based on the definition of the fire hazards, followed by estimation of direct and indirect losses. Finally, the cost-benefit analysis can be conducted based on these cost components within a framework of present light value evaluation, which can help the decision makers to select the preferred fire safety measures with the highest lifetime utility. So there are two main methods for the cost-benefit analysis. The first one is the present light value, where the Z is the total utility, B is the benefits derived from the existence of fire safety measures, C is the cost of construction or the cost of implementation or maintenance of the fire safety measures. A is the obsolescence cost, and D is the direct and indirect costs. These terms also allow an evaluation of benefit-cost ratio, which namely BCR. When it comes to the question how to choose amongst the design alternatives, the most intuitive method is to pray for the alternative with the highest BCR, which can be understood as selecting the alternatives with the highest return on the investment. However, this intuition can be incorrect, which can be illustrated by the example in the table. It can be seen that that option 1 has a higher BCR compared with option 2. However, the option 1 only results in a very limited risk reduction benefit. But the much more expensive option 2 can result in a more considerable annualized benefits. Therefore, the BCR doesn't allow to compare the alternatives, and Thus, the authority with the highest present light value is recommended, and that's why the previous described proposed methodology for the cost-benefit analysis is based on the present light value evaluation. So in this study case, a light story steel concrete composite office building is studied. The steel members of the interior gravity frames are protected with a sprayed fire-resistive material. The sprayed fire-resistive material with different thicknesses and different fire resistance ratings are studied. So as mentioned before, the proposed methodology is based on the evaluation of the fire protection cost and also the evaluation of the fire losses. Therefore, there are two types of the input parameters. The first one is the cost parameters, which are listed in the table. Table is noted here that the maintenance cost is not considered in this study. And the reconstruction cost is the sum of the construction cost, demolition cost, and disposal cost. The second one is the fire risk parameters for assessing the fire losses. Assessing the fire losses can, however, be a complex task where the fire loss statistics are not detailed enough, which is a damage area in this study as highlighted in this table here, to allow the analysis of the effect of the thickness of a sprayed fire-resistant material on structural frame members. The numerical simulations are needed to perform alongside the statistical data to evaluate expected damage in case of fire. 2D frame model is constructed in the software Sapphire for the predictive simulations. So it learned that there are many uncertainties with the fire event associated with the fire event and the structural thermal response. Therefore, to capture the effect of these uncertainties, the key parameters of the models are taken as probabilistics. One of the important key parameters in this study is fuel load. So two different fuel load distribution models are considered in the study. The first one is the one from the NFPA study, and the second one is the one from the Eurocode. And the figure here plots the evolution of the vertical deflection of the fire in the fire exposed beams at the middle span of the beam in the fire compartment. From the figure, we can say that the lack of the simulation convergences results in a rapid increase in the vertical deflection, which indicates the loss of stability. And apart from that, we can also say that the failure typically initiates in the beams. The inventory is employed in this study to evaluate different scenarios of each design. For each design, the inventory defines two scenarios: low structural failure and structural failure. The probability of each scenario is derived from the predictive simulation results, and the outcomes of each scenario are evaluated based on the statistical data and assumptions in the table, which is shown in the previous slide. The simulation results shown in the table. It can be seen that when the sprayed fire-resistive material is thicker, the failure probabilities decrease, and the failure probabilities of the NFPA study is larger compared with the Eurocode one, which is as expected due to the larger values of the fuel loads. The results of the present light value evaluation are shown in the table. From the table, we can say by using both field load distribution models, the present let values always return the positive values, which indicates the benefits outweigh costs. Therefore, under the studied conditions, these fire safety measures can be regarded as beneficial from an economic perspective. And also, both field load distribution models indicate the 3-hour fire resistance rating is the optimal solution, which actually is correlated to the prescriptive guidance that up to 2-hour fire resistance rating is typically required for the primary structural frame members. A sensitivity analysis is conducted to investigate the effect on the present let value of the assumed damage area where the failure doesn't exist. So in this study, the damage is assumed to be the entire building in case of the structural failure, and when the simulations doesn't indicate a major structural failure, the damage area is assumed to be limited to the fire compartment. And one can vary the damage area as the smoke and the large deformation can still influence the area outside the fire compartment. So from the figure, we can see that the present let values is plotted as a function of the damage area, which can be expressed as the percentage of the total floor area when the failure doesn't exist. And the beneficial impact is the largest when the damage area is the smallest in the absence of the failure. This is because even the fire safety measures can protect the buildings from falling. There are still repair costs, and as the damage area increases, the repair cost will also increase, which will decrease the beneficial impact. Also, we can say that the present let values remains positive until around 90% of the total floor area, which indicates the sprayed fire resistive material is cost efficient, and the presented conclusion is robust no matter how big the damage area is in the absence of failure. In conclusion, a rational method to support the well-informed decision is to conduct the cost-benefit analysis. In this study, cost-benefit analysis is conducted on the sprayed fire-resistive material with different fire ratings and thicknesses in a 9-story office building by using the proposed methodology based on the present let value evaluation, and which indicates the proposed methodology based on the present let value evaluation can be used for the structural fire engineering applications. Yeah, thank you for your attention. Again, if you have any further questions, feel free to contact me. And if you would like more updates, you can follow our structural fire safety engineering team of Ghent University.